Thank you, Simeon. Thank you, everybody who's joining us. So, as Simeon mentioned, we're going to talk a bit about participation tools. This work stream has been running for some time now, about 18 months. Forgive me for sharing my slide deck directly on the screen in a slightly less than perfect manner. As part of this talk, I'm going to be sharing my screen and talking you through a demonstration of some of the work we've been doing over this previous program increment. So we set ourselves some objectives at the start of this PI. Our number one objective was to develop some tools that we can use to build a low-cost scheme connection in a box for DFSPs. You could imagine, for example, somebody walking into a merchant network or a specialist reseller or even a shop on the corner of a street and buying a ready packaged box that enables a DFSP to connect and participate in a scheme, a small DFSP, like a microfinance institute, MFI, or a SACCO. As part of this process, we wanted to optimize the deployment of the SDK, our software development kit, which has a component in it known as the scheme adapter. This is a software component which abstracts away a lot of the complexity, the rigorous security, and transaction setup and orchestration required to interact with a Mojaloop-based scheme. That component has an awful lot of functionality, and it had only ever really been deployed into quite large size installations, either in the cloud, on some quite chunky, quite high spec VMs. But we'd never really tested how low a hardware profile we could get this to work on. And along with that scheme adapter, we're adopting a pattern of connectors. So you'll see in a diagram I'll share later, you'll see we use two connectors in the integration toolkit to make a technical connection between a DFSP's back-end system and the Mojaloop scheme. Those two connectors, one is a core connector and one is the Mojaloop connector. The Mojaloop connector is the new name for the SDK scheme adapter. And the core connector is an adaptation layer that abstracts away the complexities and the details of a particular core banking system. Be that one of the typical open source products that are popular with smaller MFIs and SACCOs, for example, or even a large core banking system, Temenos, for example, in use by many larger banks around the world. So we wanted to prove a real life use case to show how low we could go. We also wanted to clarify and understand the strategic imperative behind what we're doing in this work stream. So we spent a considerable amount of time thinking about what it means to participate in a Mojaloop scheme from a DFSP's perspective and from a scheme operator's perspective. So those objectives, of those objectives, this PI, we have delivered 1, 2, and 3. I will prove that to you by demonstrating our output in a few minutes. Number 4 is still very much work in progress. It turns out that it's a very complex space to think about all the different scenarios under which a DFSP might wish to participate in a Mojaloop scheme. There's been a lot of thinking done in the last 3 months, 4 months, but there's still more to come. Participation in this workstream has increased dramatically over the last few months, and I'm grateful to the members of the community, many of which are here this week, who have been contributing, so thank you. We are always on the lookout for more support, more input, particularly from people who are close to the problem, people who operate schemes or run switches. Some of you have business problems associated with bringing participants into a scheme. Some of you have technical problems associated with connecting a DFSP to a scheme. We'd like to hear from both sides. And obviously, our outputs generally usable software. So that means software engineering contributions are always welcome in this space as well. So why do we want to build a low-cost scheme connection in a box? Well, one of our mottos, one of our principles, our values is the statement, one loop for all. It's a fundamental to the Mojaloop philosophy. The small guys should be able to play in the same space as the big guys. Level playing field. Now, the Mojaloop community, over the past 6 years, I would say, have tackled on a number of occasions the complexities of integrating larger DFSPs into Mojaloop schemes. But much less work had been done to tackle the lower end of the scale. So we focused our efforts on that. And as part of our product thinking, we Imagineered, I hate that word, sorry. We created the Mojaloop integration toolkit. It's a new product that clarifies the boundaries around our software components and our documentation, tries to package up into a coherent product everything you might need to know if you're a business person or a technically focused person on helping DFSPs participate in Mojaloop-based schemes. So in there, we're starting to build best practice guidelines and documentation, software tools. The feature set is increasing quite rapidly at the moment, and we're trying to bring in new components. One of our focuses in the next PI will be to bring in some other open source components into the Mojaloop fold. But let's have some fun now. We've been running a competition, as you all know, to try to guess how many transfers we can push through a very, very small, low-cost scheme connection. So using our newly formed ITK components, running on this Raspberry Pi, it's a very small black box that you can see on the table in front of me. Feel free to come and have a look after the demonstration, by the way. Using a typical core banking system that a smaller DFSP might use. In this case, we're using MeFOS X. We know the MeFOS guys well. They're members of the Mojaloop community and have been for a long time. We're going to use the K6 load testing framework, something we also use in the performance testing workstream, to generate load and gather data on the performance of this system. It's important to note that during this demonstration, we have enabled all of the Mojaloop security features on the technical connection. That includes mutually authenticated by X509 certificates on both sides, server certificate, client certificate. In this case, using 4096-bit keys and TLS v1.2. JWS digital signatures. So we have end-to-end non-repudiation between the simulated participants. And we're using our standard ILP cryptographic hash lock condition and fulfillment. So our test use case is to send some savings deposits from mobile money accounts to MFI savings accounts. This was an arbitrary choice. We didn't have a particular scenario in mind, but this seemed like a nice, simple, relatable scenario. We're simulating 125 users, roughly, making savings deposits from their Momo wallets to their MFI savings accounts. We're going to run 1,000 transactions through this system. There's a bit more information on what the system looks like. I hope this is clearly visible. So over on the far right, we've got K6 generating our test load. We've got a scheme simulation running actually on the laptop here that I'm sharing my slides off. And I'll show you that running in a second. Then we have our bidirectional asynchronous Mojaloop API running on a wired network connection. You'll notice this is a wired setup here. So we have wired gigabit Ethernet between all the components. When we were thinking about doing this demonstration, we wanted to eliminate the the variability that might be introduced by relying on conference Wi-Fi. So I've brought along a gigabit Ethernet switch and some cabling. It's all wired. The Raspberry Pi running the ITK components, the Mojaloop connector and a core connector that's been specifically built to interact with the MeFOS X backend, which is Apache Fineract. And there's an API integration between those two. So back to the competition. We had a lot of guesses. Some people guessed a range. I'm afraid we've had to disqualify those who guessed a range because it was just too easy to win. You could specify, between 0 and 1,000 transactions per second. Yeah, that wasn't really the spirit of what we're trying to achieve, and it's just a bit of fun. The Raspberry Pi is not worth a huge amount of money. These actually, in the UK at least, they cost under $100 US. And as Miller mentioned earlier, some of the components for Raspberry Pis are manufactured in Kenya. They are available on the continent. The cost is roughly $100. So without further ado, I'm going to run my test and we'll see who wins the Raspberry Pi. Okay, I hope you can see still my screen. I'm going to try and zoom this in a little bit. Then I'll explain what you're seeing. So in this terminal window, in the top pane, I'm going to run K6 using Docker Compose. That will run K6 and an instance of the Mojaloop connector to simulate the Mojaloop hub. In the middle, you can see the log output from the ITK running on the Raspberry Pi itself. So when the transactions are running through, you'll see the log messages being written here. And in the bottom, I'm showing you a resource monitor also running on the Raspberry Pi. And this is a tool called HTOP. Some of the techies in the room might recognize this. And what it shows you is bar graphs of the amount of load each of the 4 CPU cores in the Raspberry Pi is under. So the top 4 bars here, you'll see them start to fill up as the CPUs get loaded and they start doing work. The next bar shows how much memory is being used. The Raspberry Pi I have here has 8 gigabytes of RAM. And we'll see how that memory usage goes up and down during the course of the test. So while the test's running, if you want to understand how the Raspberry Pi is performing, keep your eye on this section of the screen here. In the background, I have a resource monitor running on the MeFOS X server. This is the laptop you can see in front of you. It has 6 physical cores, which are hyperthreading, so there's 12 virtual cores. And again, this is the HTOP tool, so you can see bar graphs at the top of how busy each one of the CPU cores is. And there's the memory allocation there. So while everything's idle, it's all quite stable. Nothing much is happening. You can largely ignore the process list at the bottom, but this will just show you what the busy processes are. So the lines at the top will be the processes running that are the busiest, that are using the most CPU. The test script I'm going to run through K6 is here. I hope it's big enough for some of you to see at least some of the detail. It's a JavaScript test file. The important things to note are these 2 numbers here, VUs and iterations. VUs tells us the number of concurrent threads. They're not exactly threads because this is a slightly more complicated than that. But 12 concurrent processes will share 1,000 iterations between them. So we'll have 12 workers pulling from a pool of 1,000 tests and throwing them through the Raspberry Pi to make deposits into the MeFOS core banking system as fast as they can go. Now, This is configured so that each one of those 12 threads will send a single transfer. We'll wait for all 3 phases of that transfer to pass through before it sends the next transfer. Now, something I think the more Mojaloop savvy in the room will have spotted when thinking about your guess here. So the Mojaloop transfer has 3 phases: discovery, agreement, and clearing. Each one of those phases has 2 asynchronous calls. A message one way, and then a callback message the other way. So each transfer involves 6 messages across the wire through all of the components here. So without further ado, I'm going to start the test running. In this top pane, when the test is complete, K6 will print us a list of statistics about the test. It will tell us how many transfers succeeded, how many failed, how long it took to get the 1,000 through. That's the magic number. But also some statistics on the latency that are interesting to us when we're doing our performance testing. We won't focus on those today. We're just looking for a magic number, which is the overall average number of transfers per second that we could push through the system during the duration of the test. So off we go. So K6 is starting up. You can see at the top the Mojaloop connector pretending to be the scheme started. Now K6 is initializing itself. Everything else is quiet. Now we can see some transfers starting to flow through. You'll see these percentages go up as we run through the 1,000 test iterations. And if you look down at the bottom, you can see the Raspberry Pi is doing some work, but note how it's not fully utilized. Now I'm going to switch to our other window here, and I want you to note how the MeFOS X backend is performing. So all of the cores are being utilized. That's great. The Raspberry Pi is doing reasonably well, you might say. I'm estimating between 25 and 50% utilization on those CPUs. That's what my brain's telling me just by watching. MeFOS X is quite busy as well. We're up to 65%. Notice that the memory utilization on the Pi is very stable. It's hardly moving. Memory utilization on MeFOS X is pretty stable. We're up to 90%. Now I'm going to point out that I don't expect all of these transfers to succeed. When we were running some preparations for this, we noticed that if you hit the MeFOS backend, the Apache Fineract API, too quickly to make a deposit into the same account too quickly, it will fail the second deposit due to a concurrency violation. So the way locking is done in the Apache Fineract backend is limiting the rate at which we can send to a single account. So we mitigated that by spreading to 120 roughly accounts for this test. And you can see, we got slightly less this time, Simeon. There's the magic number up at the top there. The test's complete, 100%. So we got 10.9 end-to-end fully secure Mojaloop transfers per second through this demo setup. So 1,000 took 1.3, 1 minute 30 seconds. Now, if you do a little bit of math, you can work out that that's just under 1 million transfers per day. If an MFI averages just over 10, between 10 and 11 transfers per second, That works out at roughly 1 million transfers per day, which should be adequate, we think. Let's just switch back to my slides. So many people have contributed to this work stream. Thank you. As Spock says, my heart overflows with gratitude. Simeon, do you want to come up to the stage and we'll announce the winner? Or do you want to do questions first?
Yeah, let's take questions first.
Yeah, does anybody have any questions before we hand this piece of pie out? Miller, yes.
I noted that you had some logging going on to the screen, and that typically will put quite a drag on things. Was there anything in that form coming up from the Raspberry Pi which would have affected its performance, not the laptop side so much?
Yes, but right now I don't think the bottleneck is the Raspberry Pi, strangely enough. I would expect either the CPU to be nailed because of the compute required. The Raspberry Pi has some crypto offload on the system on chip.
Yep.
So without understanding in detail the architecture of the system on chip, it's hard to know which bits of crypto are being pushed onto the offload and what effect that might have on the CPU. The logging definitely has an effect. The Raspberry Pi storage is micro SD. Even the one that's in there is a very fast one, but it's still not as fast as an SSD or something like that. But I think the point we wanted to try to get across today is that with less than $100 of hardware, one-off cost, you can connect to a Mojaloop-based scheme, and you could, in theory, process up to 1 million transfers per day through that connection. Anybody else? Any questions? I do have one other, I've forgotten about it actually. I do have one other little thing to show you. Have we got time, Simeon? Okay. I just have one other thing to show you. Where am I? I'm on the wrong screen. Apologies. Yeah, okay. So I hope this is clear on the screen. I'll try to zoom this in as much as I can. One of the tools we built for the ITK was a very, very lightweight configuration tool. Some of you in the room might know the open source payment manager, which is a very good product for connecting to Mojaloop schemes. The Infotex and Comesa guys demonstrated how they're using that in Comesa. We wanted to go low and have a similar kind of feature set with user interface to guide people through sometimes the complexities of setting up and managing the scheme connection. But we didn't, at this stage, want to run an API and a web server on the Raspberry Pi. We wanted to see if we could keep that down to a minimum. So this is experimental. It's a little tool that I built. It lets you configure all the aspects of your scheme connection, TLS, etc., your JWS. But it also lets you manage your keys. Now, right now, the keys on the Raspberry Pi, they're on disk. There is a very low-cost hardware security module you can put on the Raspberry Pi, which, again, gives you another layer of security. But this tool, right now, will do some pretty cool things. So it will regenerate you a new set of TLS certificates and plug them into the connectors. It will generate new message signing keys and plug them into the toolkit. It will generate new ILP secrets for you using the secure random generator on the Raspberry Pi. Just wanted to show that to you. Right, sorry, Simeon. Oh, another question.
Yeah, it's me, James. Yeah,
Hi.
thank you so much for this. I think it's really impressive. So, my question is on the actual deployment of the switch on the Raspberry Pi. I'd just like to know what distribution of K8s did you use to, just run it there? And
Okay.
yeah.
Yeah, I'm not running Mojaloop on the Raspberry Pi.
Okay.
Yeah, let's keep that 100% clear. The only thing that's running on Raspberry Pi are the integration components that live in the DFSP's boundary.
Okay. Oh, yeah.
In the bank's boundary, if you like, the bank or the microfinance organization. So it's the integration layer components running on the Raspberry Pi. The switch I was simulating from my laptop here,
Okay. All right, cool.
actually using one of the integration components.
So
on the other side.
the integration components that are running on the Raspberry Pi are the ones for the DFSP.
Yes,
Okay,
exactly.
cool. Thank you.
Yeah. Yeah, in fact, like I say, the limiting factor here is not the Raspberry Pi, we don't think, because the CPU and the RAM and the I/O don't seem to get saturated during that test. So we spent a considerable amount of time tweaking things on K6 to try to generate the test load differently. But we haven't been able to load it up to maximum yet. We actually don't know what is possible. All we were able to get by a few weeks of tweaking is what you saw today.
Awesome. So we had a number of entries, and mostly for my amusement, I'm going to go through each one of them. Irakoze from Wiredin guessed 47 transactions per second. Superwood, not sure where from, 2,000 transactions per second. Ishimwe from RSwitch, 500. Francis from Higala, 15. That's close. Bonaparte from Wiredin, 60 transactions per second. Maximilian from Wiredin, 300. Derek from IPS, 130. Patrick from Wiredin had 40 transactions per second. Anthony, not sure where this is from, 5,000 transactions per second. Marie-Pierre, 55 transactions per second. Brian Joroge from KPMG gave a range, 8 to 10 transactions per second. Dennis, that's disqualified.
That's a good consultancy answer.
That's it's KPMG, they give a consultant's answer. Dennis from KPMG also give a range 7 to 8. Eddie Kanyiganwa from Carnegie Mellon, he's doing his master's there, guessed 7. Pretty close. Mamadi Africanenda guessed 70,080. It's a very specific number. Majumo from Zekel, 170. Osman Jallo from Gamswitch, 41. Elijah Okello from Infitex, 200. Yosef from Comesa Business Council, 1,000 to 2,000 for simple transactions, 10 to 100 for complex transactions. Babukar from Gamswitch, 83 TPS. Festus Were from IPSL, 300 TPS. I'll skip the winner. Samuel from Carnegie Mellon, CMU, 15 transactions per second. Marcus Davis from CBI, 13 transactions per second. Alan, 150 transactions per second. Kelvin Joroge from IPSL, 75 transactions per second. Azim from Paces, 65 transactions per second. Shashi, 15, which is his lucky number. David Higgins online, that is 17, is his guess. Jane Stroken gave the sum of life, the answer to the sum of life, 42. And yeah, Azim said 60 to 65. The correct answer we saw was roughly 10.9, 11 transactions per second. The closest answer was given by the CEO of iJane, Akim Chisha. He gave 12 TPS. Is Akeem here? All right. So now you know which system integrators to work with.
Thank you, Simeon. Yeah, thanks, everybody. If you want to come and join us in this work stream, we'd love to have you. There's details on the screen now of my email address, or on Slack. You can reach me on that Slack channel.